In this video, we shall discuss the expectation and variance for binomial distribution of the moment generating function. For more on this topic, you need to subscribe to this channel. Of course, we should recall that the moment generating function for the binomial distribution is given as PET plus Q raised to the power of n. So we shall use this to find the expectation and variance for the binomial distribution of moment generating function. The expected value of x is equal to the first differential of the moment generating function at t is equal to 0. So if we differentiate this, we put it at t equal to 0, then we get our expected value of x. It then means that our expected value of x is equal to the first differential of this. Now, how do we differentiate this? We use what is called the function of a function method of differentiation to differentiate this. If we differentiate this, we get n into PET plus Q raised to the power of n minus 1. Since we are differentiating with respect to t, we also differentiate what is inside here. So we have PET. Of course, this becomes our first differential or first derivative for the moment generating function of the binomial distribution. Now, at t equal to 0, our expected value of x will now be equal to n into p. Anywhere we see t, we put 0 plus q raised to the power of n minus 1 multiplied by p e raised to the power of 0. That means exponential 0. Now, we should note that anything raised to the power of 0 is equal to 1. So anyhow we see e raised to the power of 0 or the exponent raised to the power of 0, we put 1. So we have that our expected value of x is equal to n into p plus q raised to the power of n minus 1 multiplied by p. We also recall that from probability, we have that p plus q is equal to 1. So it then means that our expected value of x is equal to n into 1 raised to the power of n minus 1 multiplied by p, which is equal to, this will give us 1, which will give us np. So our expected value of x is equal to np. So our expectation or the expected value of x for the binomial distribution is equal to np. The next thing to do is to look for the expected value of x squared. And the expected value of x squared is our second derivative of the moment generating function. Second derivative of the moment generating function at t is equal to 0. So if we differentiate this at t is equal to 0, we now get our expected value of x squared. So we should recall that our first moment or first derivative is n into PET plus q raised to the power of n minus 1 multiplied by PET. So what we do here is that we use what is called the product rule of differentiation, u and v. We use what is called the product rule of differentiation to differentiate this to get our second derivative. Now, it then means we can write our expected value of x squared, which is the second derivative of the moment generating function, to be u dv all over dt, because we are differentiating with respect to t, plus v du all over dt. So we use the product rule. This is the product rule formula. We use the product rule to differentiate this. That means we come over to this place. Now, we have that our expected value of x squared. For more on this topic, you need to subscribe to this channel. Our expected value of x squared, which is the second derivative of the moment generating function, is equal to, now we have u, we bring down u is n into PET plus Q raised to the power of n minus 1 multiplied by dv all over dt, dv all over dt, dv all over dt. So we differentiate this with respect to t. If we differentiate that with respect to t, we get multiplied by PET, we get that same thing, plus we have v is PET, that means p multiplied by exponential t, multiplied by du all over the t. So we differentiate this again, du all over the t. If we differentiate that, we get multiplied by n into n minus 1 into PET plus Q raised to the power of n minus 1. It's supposed to be minus 1, which is minus 2. So we'll have minus 2 multiplied by, we'll also differentiate what is inside. Yes, which is PET. So this is what we get. Now, at t equal to 0, we have that our expected value of x squared is equal to, anywhere we see t, we put 0. We have n into PE0 plus Q raised to the power of n minus 1 multiplied by PE0 plus PE0 into multiplied by n minus 1 multiplied by PE0 plus Q raised to the power of n minus 2 multiplied by PE0. Of course, we note that we say, but anything raised to the power of 0 is equal to 1. So anyhow we see the exponent raised to the power of 0, we put 1 there. So we have our expected value of x squared to be equal to n into p plus q raised to the power of n minus 1 multiplied by p plus p multiplied by n into n minus 1 into p plus q n minus 2 multiplied by p. So this is what we get. The next thing to do, we move over here to get our expected value of x squared. For more on this topic, you need to subscribe to this channel. So we come over to this place so that we can get our expected value of x squared. We should also note that our expected value of x is NP, because for we to look for the variance, we will have to recall this. So put it at the back of our hearts. Now, we come over here. We say, but from probability, we have that P plus Q is equal to 1. So it then means that anywhere we see P plus Q, we put what? 1. So we have that our expected value of x squared will now be equal to n into 1 raised to the power of n minus 1 multiplied by P plus P multiplied by n into n minus 1 into 1 raised to the power of n minus 2 multiplied by P. So this will give us np plus n into n minus 1. P multiplied by P is P squared. So we have our expected value of x squared to be this. The next thing to do is to find the variance. How do we look for the variance? The variance of x is equal to the expected value of x squared minus the expected value of x all squared. This is how to look for the variance. We also need to recall that our expected value of x is equal to np, and our expected value of x squared is equal to np plus n into n minus 1 p squared. Now, the next thing to do is to substitute what we have for our expected value of x and our expected value of x squared into the variance. It then means that our variance of x is equal to expected value of x squared is np plus n into n minus 1 p squared minus bracket np squared, which is also equal to np plus n into n minus 1 p squared minus n squared p squared. So this is what we get as our variance of x. So we have to resolve this mathematically. We come over to this side. So it then means that our variance of x. For more on this topic, you need to subscribe to this channel. Now, we have this will go into this and this. So we have n into n minus 1 p squared minus np, which is also equal to, we can open this bracket to give us n squared minus n into p squared minus np, which is equal to n squared p squared minus np squared minus np. Of course, this also can go into this. This is our variance of x. This is our variance of x. Our variance of x will now be equal to, this cancels this, so we have np minus np squared. So we have something that is common, which is equal to np into 1 minus p. We should recall that to say, but if p plus q is equal to 1, it implies that q is equal to 1 minus p. From probability, q is equal to 1 minus p. It then means that if we have 1 minus p here, 1 minus p, it then means the whole of this is q. So we can write it as our variance of x to be equal to np. We now substitute this q into here, npq. Hence, our variance of x is npq. That means our variance for the binomial distribution for the moment generating function is npq. Our expected value of x is np, and our expected value of x squared is np plus n into n minus 1 multiplied by p squared. So this is how we can obtain the expectation and the variance for the binomial distribution for a moment generating function. For more on this topic, you need to subscribe to this channel to get more tutorials on moment generating function.